Okay. How's that? Great.
What's that?
All right, guys, listen up.
Scalpel. Oh, you're starting.
Today, we're going to be talking about, Tyler, do that quietly, please, have a seat. Today, we're going to be talking about fish evolution, okay? We could spend days, months, walking through all the believed or perceived steps of fish evolution from beginning of time to today. Obviously, we're not going to do that. We're going to try and do it in like 20 minutes. So I'm just giving you the major bullet points that are believed to be the key events in fish evolution from the first fishes to today. All right? A lot of this is, not a lot of it, but some of it is certainly speculation. They go by the fossil record and by what we know. A lot of these are, there are some blanks to be filled in here, but I'm going to kind of tell you what we do know about how fish got to be the way they are today and how they got to have the adaptations that they have today, and that's what I really want to focus on. Okay? So the first thing to know, we're doing fish evolution, are that fish are very important in the evolutionary history because they're the first known chordates. Who remembers from last time when we talked about classification what a chordate is? Phylum Chordata. Notochord. They have a spine. Very good. Thank you, Zach. Nice work. Give Zach a round of applause. Oh, really?
Settle down, guys.
So fish are the first known chordates, meaning they're the first known vertebrates, and therefore they're very important if we're talking about vertebrate evolutionary history. Okay, first known true chordates. Okay, and they're believed to be over 500 million years old. Okay, we all know that MYO or MYA, million years ago, million years old, whichever it is, they started evolving somewhere around 500 million years ago. Okay? So they're pretty old. And we're going to kind of walk through how then this has occurred and what major groups have arisen and have stayed, what major groups have arisen and gone extinct over the last 500 million years. Okay? That's what we're focusing on. Now, well, they started evolving, or they came to be 500 million years ago. Most evolutionists leading current species, excuse me, on your paper it says most evolution leading to the current species that are here in today's oceans happened somewhere around 3.5 to 5 million years ago. So current species started okay. That's a big gap from 500 million to 5 million. Okay? Those 495 million years saw a lot of changes happening to what we would call our ancestral fish species. Okay? I'm going to try and wrap up 495 million years now into 14 minutes or so. Okay? So keep that in mind. Massive amounts of information that are just going to be skipped over here. And I know that. Okay? Now, what's interesting, and the first thing we have to understand for fish evolution is that there's a fundamental counterintuitive fact about fish evolution. If I were to ask you, which do you think evolved first? We know that life began in the oceans. So which do you think evolved first? Freshwater or marine fish? Marine would be the intuitive answer, but that's wrong. Most of our current fishes evolved from freshwater fish. So life started in the ocean, they started to evolve there, at some point moved into freshwater, there was mass extinctions in the oceans, and all the freshwater fish rehabitated all the niches of the marine fish. So current day marine fishes evolved from freshwater fishes. Okay? That's why it's counterintuitive. You'd think that it would go the other way around. Life starts in the oceans, we know this, it evolves, blah, blah, blah. You think the fish that were still there would have started there. That's not true. Okay? So fish evolution, counterintuitive, because it goes ocean to fresh water and then back to ocean. And this is our current fish. Okay? Now, the mass extinctions, everything else that happened that caused this, we're not going to talk about that right now. You've heard of things, though, like, hopefully in biology, you guys talk about stuff like the Cambrian explosion, which was a massive amount of especially vertebrate species that kind of all came about in a relatively geologic short period of time. Okay, all those are happening to lead to this, but it just is kind of weird. It doesn't really make sense. All right. Currently today, there are approximately 24,000 species of fish. So this process has led to fish becoming the most abundant vertebrate on Earth. Fish are the most abundant vertebrate on Earth. There's nothing else that comes close. The next most abundant species is birds, of which there's something like 8,600 different species of birds. Okay? So you got 8,000 to 9,000 birds, then you jump to 24,000 species of fish. So obviously they've been very successful. Something in this time period, this 495 million years, okay, has led them to be immensely successful and fill their niches very well. Now later on in the year, we're going to be talking about some things like climate change in the Gulf of Maine and overfishing and fishing practices. We're going to talk about why it will be a real travesty if 495 million years lead to these species being so amazingly adapted to their environment, and then we kill them all off. Okay, that would be bad news, especially since current rates say that we're going to do it in about the next 30 years. All right, but that's later. For now, let's focus on the positive and simply look at how these adaptations came to be. Okay, so it all started with the first fish to evolve. First fish. Okay, the first fish to evolve. Now, these are some big Latin words. Don't make fun of me when I mispronounce them. Now, the ironic thing is you won't actually know if I'm mispronouncing them. Okay? But I'll know that you'll know. Okay? The first fish to evolve were the agnathans. Okay? Agnathans. Okay? Or class Agnathia. Agnatha. And these were jawless fish. Okay. With no jaw, they had simply a rounded mouthpiece. They still have. There's two species, which we'll talk about in a second. They're still alive today. But these were the original fish. All right, and we had however many hundreds, thousands species, basically, of these fish way back when, you know, hundreds of million years ago. They were jawless, and they had a rounded mouth part that could either, if predatory, basically suck blood or protein or juices or whatever in a either predatory or parasitic method. Okay? Or they could be modified for filter feeding. They could kind of float around the bottom and suck up all the algae and whatever else was on the bottom of the ocean floor. So rounded mouths for either or filter feeding. Okay. Today, there are two species left, lampreys and hagfish. Okay, and I want to talk about the hagfish a little bit more in just a second. But now, without big, heavy jaws, right? You picture a shark, and you're like, well, what does a shark have to worry about? It's got a big jaw to fend itself off. Fend itself off. Fend other things off. Fend predators off. Fend whatever. Okay? These guys didn't have that. So what did they have? They were heavily armored. It's spelled the British way. Armored. Okay? Heavily armored for protection. And indeed, they developed other specific adaptations for protection, of which the hagfish I'm going to show you a video of. Okay? Have any of you ever seen any of the videos on the internet, interwebs, of hagfish and their sliming mechanisms?
Yeah.
You have?
I've seen pictures.
Yeah, it's amazing. I'm going to show you a video of that right now. Hagfish today are still alive, okay? And they have one of the most unique adaptations for protection of any animal in the animal kingdom, okay? And what they can do is they create this massive amount of slime, all right? I'm going to show you 2 videos detailing this. Come on. Do this one first. Okay?
Okay, yeah.
Okay? What they're doing here is this is a hagfish, right? And this scientist is basically extracting I believe it's one of the glands, or in some way extracting the slime-making cells. I honestly don't know how it's done, but they're extracting that from this, and they're going to introduce it to this beaker. This is just water right now. Okay?
I'm collecting some slime.
So it's just the slime.
Yeah, you see? Oh, yeah. Mix it. My official mixing apparatus, let me hold it up.
Okay, so he's scraped off some of the just simple slime from it, and it reacts with the water. Look at this. Watch what happens now when he takes it out. Okay? And that's it. There's nothing left. There's nothing left in the beaker. Okay?
It is empty. Turn the beaker upside down and pour it out. Nothing.
Okay? So this slime that the hagfish emit, when put in contact with water, just multiplies and maximizes. Alright? And that's especially evident, or how is that useful, especially evident, if you watch this video. This was just captured in 2009, 2010. They had known for years that hagfish developed this slime. It was assumed that it was a defense against predators. You try and bite the hagfish, and you just instantly get this mouthful of disgusting, snotty slime. New studies show that they now believe that these hagfish can actually use this as a predatory mechanism. So new studies are suggesting that now these hagfish can go find their food, actually kind of secrete this slime enough to envelop and kill their bait, the bait fish, not bait fish, their prey, that's what I'm looking for, okay? And then feed on them and eat them, okay? And they got this amazing underwater shot. We're not going to watch the entire 3 minutes. I'm just going to show you the first part, the first 2 parts, all right? This is filmed off the coast of New Zealand. This is the first official video that I know of that actually shows the hagfish in its natural environment. You can see it in like the lab. They shake it up like they did before, okay? But here's a hagfish feeding on this bait bag, and here's what I believe is, I don't know what, I thought it was a Greenland shark, but I don't think it is. I don't know what kind of shark that is. That kind, whatever it is, right? And it's snooping around. Here's bait. The hagfish is totally just minding its own business, feeding on the bait, okay? It's got that rounded jaw. Here comes a shark, and the shark's like, easy meal, and it grabs hold of it, and then immediately you can see all this slime, and in fact, that shark, they believe, dies right now. It's so enveloped with the slime that it clogs up its gills, right, and it can't, see it's trying to shake it all off, it's all done. Now watch this. Similar, looks like some sort of bass-like species, ray finned, okay, and it's instantly covered in the slime. And what does a hagfish do? Absolutely nothing. It continues feeding, okay, as if nothing had happened, right? Here it comes again, gonna eat it, oh, alright, it coughs it out, and it's covered in slime, and now the fish spits, and see, it's still got the slime trailing off of it, alright, it's very unhappy, okay? So it's pretty cool, and this is a pretty amazingly developed defense mechanism for what is evolutionarily a very, very, very old species. These hagfish are the, ancestors, basically, of some of these first fish, some of the first vertebrates. Okay? All right. The last part shows them, I'll fast forward a little bit. This is them putting the thing in the water. All right? It shows, back here, it shows them using it. This is the hagfish. It's secreting the slime. You can't really see it, but what's happening is it's secreting the slime down here. And I believe this is the video showing it killing off, basically, the little worm or fish that were in the bottom and then eating it. Okay? And if you've done the reading, you know hagfish get their own slime off their body by tying themselves in knots, which is what it's doing here. And it ties itself in a knot right there and works the knot down its body until it squeezes off all this excess slime off of its own body. And then it goes on its merry way here. There's the knot. Okay. And it's gone. And you get all this slime here. Okay? And then it swims off. Okay? So, hagfish. Very cool. And a name that, is just so easy to love. Okay? So heavily armed for protection. Hagfish, they have this slime. Okay? Which is a specific adaptation. Any questions on this? This making sense? Basically what I'm trying to get at, the general take-home message here, is that even millions of years ago, there were such specific adaptations that were being developed. Okay? That hagfish has an amazing ability for protection. Right? That slime is so unique in the world. Okay? And it's being studied for all sorts of things. All the other videos on YouTube that I found, if you ever want to go look at them, mostly show hagfish in like the lab at big universities because they're studying this slime, trying to see what they can do with it. Okay? So, that was class Agnatha, okay, the agafish. Those were the first fish. Okay? We're going to move on now to jawed fish, okay? The opposite. So one, we're here, we saw the video. So next came jawed fish. Okay. Now it's believed that jaws evolved only once. So probably there was some remote common ancestor who developed a jaw rather than through parallel evolution, coevolution, there being a series of species that evolved jaws. They think it just happened once. Okay? And fish jaws are actually amazingly complex compared to human jaws. Okay? First thing on your paper it says, jaws evolved from gills. So somewhere, these agnathans, somewhere, some relative of them, okay, they had gills, they had the rounded jaw. At some point, those structures from the gills were connected to some bones in the head, and eventually those led to the first working jaws. Okay? Now humans have only one bone in their jaw. Right? Got your jaw, connects up here, okay, and this is your jaw. You can get a human jawbone, right? Just detaches. One bone, very simple for chewing, all right, and all the things, right? Fish, jawed fish, can have over 24 bones in their jaw. Okay? Different fish species have different amounts, but some have over 24. So they're amazingly complex, right? Now the evolution of jaws was a huge leap forward for fish because suddenly it allowed them to do many things that these guys couldn't do, namely hunt better, okay? And if they're able to hunt better and they're able to get more food, okay, more energy, that leads to less muscle density, so they get smaller, lighter, okay, or not necessarily smaller, but lighter, less density, okay? They're more agile, right? And so this evolution of the jaw is what leads fish to then start looking like they do today. Okay? And the first, there's going to be, I said like there's 2 more lectures. I want to talk about shark evolution separately I do want you to note that somewhere in here, okay, somewhere in here, the class chondrocytus. Let's say that. So you say, I send your notes, somewhere in here, class blank begins to evolve. That's the sharks, rays, skates, all of those. We're going to ignore those for a second. But they're technically the next group to evolve. But we're going to skip right ahead, right? Let me spell this out. Never spell this. Can't write it out either.
Chondrocyte.
Dice. Yes.
Chondrocyte.
I just call them the chondrocytes.
Wait, is that a Y or a T?
Chondrocytes.
Yes.
Okay?
It's chondrocyte. Yes.
Where do we write that?
It says, somewhere during this time period, class blank evolved. That's where that goes. And now we're going to skip over that, because that's a separate lecture. We're going to skip right to the bulk of modern fish. Or the true bony fish. Okay? They evolved next. So really we've gone through three groups. You've got the original jawless fish, then you've got these guys, which is the cartilaginous fish, the shark, rays, skates, which we're skipping. And now the third major group that we're talking about are the modern fish, or the true bony fish. Then when you guys think of a fish, this is what you think of. Bass, salmon, all right? Tuna, perch, goldfish, sunfish. Anyone else want to throw any more fish in there? Minnows. Good job, Zach. Okay? All of those are the true bony fish. Or, there's another one that I have to spell here. Okay? Osteichthyes. True bony fish. Good. Okay. Now these guys started to evolve, but didn't fully rise in numbers. Oh, and they were around 410 million years ago. So they started to evolve, but they didn't rise in numbers until all those other, the sharks, the megalodons, all the other chondrocytes and everything else that were around, they started to decrease in numbers, and that's when the niches opened up for these bony fish to really take over, okay, and become as populous as they are today. All right. Currently, there's about 19,000 of those 24,000 of fish are these guys. Okay. So the bony fish alone are more than twice as numerous as the next vertebrate species or the birds. Okay. So they didn't really rose in number when large sharks and placoderm, which is a group that we didn't talk about before. Okay? And the key bit about the true bony fish is that they have the swim bladder that we talked about last time. Okay? All bony fish have that swim bladder that we talked about last time. Okay? We're getting there. We're almost done. I know this is gripping stuff. I can tell by your faces that this is the most exciting thing you've ever done is talk about bony fish. Okay? Bony fish are broken into three groups. Okay? First, what you're probably most familiar with are the ray fins, the ray-finned fish. And this is the tuna, salmon, bass, all those ones that you usually think of as fish. Those are probably the ray-finned fish. Okay, they're the most common. Right? Freshwater, saltwater, all are ray-finned fish. Okay. Most common, most abundant. Right? We're going to do a dissection of these next week. Okay? Not all of them, but your common fish that you get, that you eat, that you find at the fish market, ray-finned fish. Okay? But there are two other groups, much less common, but equally important in terms of evolutionary history. Okay? And these, the second group, are the lungfish. Okay? They're freshwater only. There are no in the marines, but I'm going to talk about them just for a second. Because they can get up to 90% of their oxygen from the air. What? No way, Mr. McCullough. That's crazy. 90%. I don't believe it. I wonder if I say that with my back to the camera, if it will sound on YouTube like you guys are all saying that. Wow, Mr. McCullough. That's so interesting. I didn't know that. Okay, 90% of oxygen comes from the air. Okay? And these guys then are incredibly important when we start hypothesizing about how fish moved onto land to become amphibians, which we know happened at some point in there. Okay? And it was probably some way connected to these lungfish. I believe you guys have heard of the snakehead infestations down south from Georgia to Maryland. I believe, and if the snakehead is not a lungfish, it's very similar to a lungfish. Okay, but that's the type of thing because it can actually stay out of land. Most fishes stay out of land. It can stay out of water for extended periods of time and actually move from body of water to body of water. They're voracious hunters, the snakeheads, and they're decimating a lot of the bodies of water down south of natural game, the trout, the bass, whatever it is. Okay, so these lungfish are the second group then of these bony fish. Okay. And then finally, the third group are the most rare, but also very important evolutionarily. That's why we're talking about that. And these are the lobefish. Okay? And they were thought to be extinct for a long time. Until 1930, a live specimen was found, I believe, in the Indian Ocean. And the lobefish are incredibly important evolutionarily because they don't swim the same way as the ray-finned fish, or I believe as a lung-finned fish. Okay? Everyone hold up your hand and show me how a fish swims. Wow. Zach is on fire today, guys. You guys could all learn something from Zach. I mean, he's really getting this. Yes. Okay? Ray-finned fish, they all go like this, right? Look at the guppies over there, right? You picture any fish you ever seen, they go like this. Yes? Is it really? This means fish in sign language? Learning something new every day.
Wow.
Okay? We're in science. Who knew? Okay? It makes sense.
Flabbergasted.
Okay? Lobefish don't do that. They don't move their tail that way to move. Instead, they take each of their fins, the bottom, and they move them kind of like this. Okay? And then do the other ones like this too. Okay? Why do you think evolutionarily that kind of triggers something? Or why should it trigger something? Instead of doing this, they do this with their fins. Say it, Zach. You're on fire today. It's like walking, okay? These are believed to be the first fish to somehow evolve the ability, perhaps combined with something like this, to get up onto land. And these became the first terrestrial vertebrates, okay? All vertebrates on land, land animals, came from fish, probably from these lobefish. Then they went extinct, but there are some still around today. Okay, they're very rare, all right? But that's incredibly important evolutionarily because the difference between this and this, right, might not seem like much, but physiologically, anatomically, very important, okay? I know that's how you swim, Zach. Fish paddle, okay? So these are thought, some thought, to the first land vertebrates. Questions? Okay, two final things then. We've just done 495 million years of evolution packaged into basically a few key bullets. Okay? The take-home message for you guys that I want is the incredible diversity that has come from this evolution. That these ray-finned fish and everything else now are the most abundant vertebrate species, and because of their adaptations, they've been able to fill so many different niches in marine environments for us, but also freshwater environments. Okay? That's what I want you to take home. As an add-on, I will mention that there are several theories of thought about how exactly, though. We know that these evolved first in the water, and that these then led to terrestrial animals. How did these turn into a wolf? How did these become, all right, whales? Whales are actually, we'll talk about them later, they were marine, and they went on land, and then they're back in the water. Okay? Well, they weren't whales when they were on land. They were like some sort of cow-like animal, and they went back in the water.
That's a big cow.
Yes. Yes. Okay? There's two, just very briefly, two schools of thought. One was introduced by a guy named Alfred Romer. Right? Alfred Romer. Always a hard guy to find. He just roamed around. Okay? Alfred Romer. Thank you. Okay? This was in the 1940s. Okay? He suggested in the 1940s that in a drought, okay, when those water levels are receding, okay, he suggested that lungfishes, or fishes that had some sort of adaptation that allowed them to come out of the water a bit, okay, he believed that in a drought, lungfish came up on land, okay, and were able to utilize then new resources found on land that were becoming scarcer in the waters because of these droughts, okay. So in drought, lungfish came to land. They then passed on these significantly important adaptations to their offspring. And over time, then, fish started becoming more and more acclimated to these droughts and coming up on land. Okay? Passed on traits to offspring. Okay, and then these offspring, okay, had modified fins, which became limbs. Okay? Now, in Romer's interpretation of this, it's the drought, it's the environment, it's the external pressures that are forcing these fish up onto land. Okay, and that was significant. He's saying that during droughts, that's when they came up, and that was important, droughts were happening. Since Romer's time, in the 1940s, other theories have come up that have the basic same gist of it, basically that fish with modified limbs for climbing up on land came up on land. But their theories, the other theories, state that instead it was competition in the oceans that drove the fish up there. It wasn't drought, it wasn't anything like that. It was the fact that the ocean was getting so full of fish that some of those fish, or excuse me, fish were becoming so successful that they were having tons and tons of offspring with lots and lots then of genetic variation. And that genetic variation led to modified fins, which allowed these fish to then get up on land and find these new resources that were being depleted in the oceans. Okay? So other theories, tons of fish offspring equals lots of fish equals fish competing equals fish on land. Okay? Both of these theories have merits. In reality, there's, the evolution, the fossil evidence, I'm forgetting the name of it now, is discovered in the late 90s, early 2000s, shows a fish that would fit this, from the time period, that would fit this theory a little bit better than this theory. So now, most evolutionists kind of go by this, but really the key fact here is that modified modified fins turn into limbs, came up on Earth. Up on Earth. You know, I get tired towards the end. One last thing I want to show you. Okay? Well, you guys aren't going to see that at all. Okay? This is just kind of showing the overall evolution, right? You can't read these, so I'm going to read these kind of to you. Here are tetrapods. These are vertebrate land animals. Okay? They came around right about here. Okay? Carboniferous, somewhere around this time period they evolved. Okay? Previous to them came all these: the lobe-finned, the lungfish, the ray-finned. Okay? Jawless fish, those were the first. Okay? Placidonternus, which is entirely extinct now. The shark rays, all right, all came here. So you can see that all these came before the tetrapods started. However, ray-finned fish that we think of now happened somewhere around here, right about with the same time period as the tetrapods. Tetrapods started to expand a little bit earlier, but the ray-finned fish started earlier. Sharks and rays, almost unchanged. We'll talk about that later. Okay? Lobe-finned fish, almost all gone. Lungfish, almost all gone. Okay? All these other guys almost gone. These guys gone. Jawless fish, 2 species now left, lampreys and hagfish. Okay? But it's tetrapods and ray-finned fish that have expanded greatly within the last, 50 to 100 million years. Okay? Dinosaurs, right? We're all here. This is dinosaurs. Okay? Just want to show you that. Okay, any questions? All right.